Hi everyone! In today's episode, we're going to explore how to add artificial intelligence, or AI for short, to the car we've been working on for the last couple of videos. To start, let's look at the car which is approaching a turn. Last time, we created the car sensors too. The idea will be to create a better version of our car, a smarter one, a car with a brain. The brain will use different sensors to judge what the car should do next, in this case, steering right. This is how I defined the smart car class. It's as simple as a car with an additional property called the brain. Under the hood, that brain is what we commonly name as a neural network that looks like this. A lot of circuits or neurons that are connected to each other to mimic a biological brain. Keep in mind that a biological brain is way more complex than neural networks though. In this neural network, we should distinguish few things. The first part is the input layer. It's a bunch of values that we will feed to the network so it can predict what to do next. In our case, this input layer will contain the values of the car sensors, the velocity, and the heading angle. On the right side, we will have the output layer. This layer will contain the prediction of the network. In our case, we will have two predictions. First value to decide in which direction the car should steer, and the second value will decide in which direction the car should go. Between these two layers, we will have a bunch of other layers that we call hidden layers. The number of the layers and neurons per layer are something to decide on your own. The more hidden layers and neurons you have, the more complex your network is. Of course, there are a few architectures to follow depending on your need. Each neuron affects neurons on the next layer through what we call weighted connections. The same thing is applied across all neurons and layers until the output layer. Each time, the network will receive some input values, does some math with these values that will activate the neurons on the next layer, and so on. Now, let's have a look at how this is really working. We'll use a neural network with two neurons on the input layer, a single hidden layer H with three neurons H1, H2, and H3, and an output layer O with two neurons O1 and O2. We can consider these layers as matrices with a single column and n rows. We can refer to them as column vectors as well. We said that neurons are connected to each other through weighted connections. We can translate this sentence and say that each vector is calculated based on the previous one. To start, the vector H is the result of multiplying the vector I with another matrix W1 that defines the connections between the neurons. First row of the matrix will contain W11 that defines the connection of I1 to H1 and W12 that defines the connection of I2 to H1. Second row will contain W13 that defines the connection of I1 to H2 and W14 that defines the connection of I2 to H2. Last row will contain W15 that defines the connection of I1 to H3 and W16 that defines the connection of I2 to H3. We can notice that the shape of the weight matrix is defined based on the shape of the two column vectors I and H. The matrix will have two columns because we have two neurons in I, and it will have three rows because we have three neurons in H. Following matrix multiplication rules, H will be then a column vector, where H1 will be equal to I1 times W11 plus I2 times W12. H2 will be equal to I1 times W13 plus I2 times W14. And H3 will be equal to I1 times W15 plus I2 times W16. Also, we need to add some constants that are known as biases to these weighted connections. This is done in order to be able to add few adjustments to the result to fit the prediction with the data. To calculate the column vector O, we will basically repeat the same process. O will be equal to another weight matrix W2 multiplied by the previous layer H plus a second column vector called B2 for the biases. If we take a moment and look at these equations, we can notice that both equations are linear. In a nutshell, no matter how many hidden layers we attach to this network, all layers will behave the same way, because the composition of two linear functions is a linear function itself. Unfortunately, neurons cannot learn with just a linear function attached to them because there are so many problems linear transformations can solve. We have to find another way to introduce non-linearity to our network, so it can actually learn things and be capable of performing more complex tasks. This is why we need an activation function. When it comes to choosing one, there are actually so many options to pick from, like logistic function or sigmoid, which for small inputs it results in an output of 0, while for large inputs it results in an output of 1. Rectified linear unit or ReLU, which behaves like a linear function for positive numbers and outputs 0 otherwise. And hyperbolic tangent, which is actually a shifted version of the sigmoid function. To get back to our network, all we need to do is to apply the activation function like so. So now, after having a look on what a neural network is and the relation between different layers, what are the actual values we should use for weights and biases? The answer is randomness. In fact, you can consider all of these values as knobs or controllers that are randomly initialized. The ultimate goal will be to find which values are best to use so our model is able to solve the problem. Obviously, tweaking these values on our own will take so much time to do. Instead, we will let the computer do it for us. And that is what we actually call machine learning. Let's have a look at the neural network code now. First, I need to create the shapes of the weight matrices based on the layers we have in the network. Then, for each shape, we generate a matrix with random numbers going from -1 to 1 inclusive. We will be doing almost the same thing for the biases, except we need to create column vectors in this case. For the prediction, we get the input as the method argument. Then we apply the steps we saw previously. Each time, we multiply the column vector by the weights and add the biases. Then we pass the column vector through the activation function and keep feeding the output to the next layer. At the end of the loop, the output will be the network prediction, so we can return that. The activation function I'm using is the hyperbolic tangent. Now we need to override the update method for the smart car class. We first call the super update method, which will update the car coordinates and heading like before. Then we call the predict method. I have also given the car a maximum lifespan and a check against inactivity. If the car doesn't progress on the track for 50 consecutive frames, we will kill the agent. This way, we prevent being stuck during the training process. The car's predict method will mainly gather all needed inputs, in our case the velocity, the heading, and the sensor's values, and feed them to the neural network. And based on its prediction, we will decide which action the car should execute. Now, let's go back to the game and give our smart car a try. Okay, this is not smart at all, so we need to start training our network. But this will be the topic of the next video. Thank you for watching and see you next time.